So today we're starting a new unit. We will not have the test over this until not for a while. So it's after the time change. How's that? Again, vocab at the beginning here, so you can check that out later on. So the homework for tonight is the ones, and it's pretty straightforward, pretty simple. Hopefully you can figure that out after we do an example. What I want to talk about starting off today is waves. Okay, because we'll be talking about waves for the next couple of days, and you'll be doing calculations with waves. You'll also have a quiz about waves here in the very near future for most of you. So a couple things about waves. Number one, the frequency. Guys, please listen. The frequency is the number of waves that pass a given point per unit of time. So, for example, if you decide to wander out into the ocean and carrying a stick with you, and you stick the stick into the sand and you count how many waves hit that stick per unit of time, that is frequency. So if you're on a nice, calm day, not too many waves are coming by, but if we have like a hurricane or a storm coming in, you're going to have a lot more waves coming into the action there. Okay, so the frequency is higher when you have more energy associated with your wave. Okay, so when we talk about frequency, it's how many waves pass a given point per unit of time. Now the time that we're using is in seconds, and I thought I had, oh, here it is. So when we talk about energy, or I'm sorry, the unit is going to be 1/seconds, also known as a hertz. Now, some of you may have heard of a hertz from like Hertz Rent-A-Car or Hertz whatever. I don't know where they got that from, but
she goes, that's ketchup.
That's Heinz.
No, it's not. Sorry.
All right. Also, when we talk about hertz, the unit that we'll be talking about looks like a V. And you'll see me represent it like that. And that's the Greek letter nu, which looks like a V to you and me. Okay. So that represents frequency. And again, the unit for frequency will always be in 1/seconds. Now, some of you might say, is 1/seconds the same as seconds? No, it is not. Okay. This is actually implying, the one up here implies waves, but we don't say waves. Yeah, so how many waves per unit of time is frequency? Okay. When we talk about wavelength, so when we talk about wavelength, some of you have already talked about waves in the past. The length of one wave can be used as either from crest to crest or from trough to trough, but I like to think of it as where we start here, go up, come all the way down, and then go back to the starting point. Now, generally in chemistry, they don't do that because it's not as easy to see that midpoint, but they like the top of the wave or the bottom of the wave. But I will do it that way for the most part. So one wavelength is you start somewhere, you go all the way up, all the way down, and then return back to your original starting place. That is one wave. So if I were to ask you which one had more waves, let's say we call this A, we call this B, obviously B has more waves because it has more up and downs than this one on the right, or left, sorry. The length is larger in A than it is in B. Now, one thing that we don't talk about in here, but physics loves to talk about, is amplitude. Amplitude is the height or the depth of a wave. So how high is a wave or how low is a wave? That's amplitude. We don't deal with that in chemistry. All we deal with is how long is that wave or how short is that wave or how many waves pass a given point per unit of time. Yeah, Matt?
So, like, when I was in ICP, we didn't learn this to, like, the physics unit. Why is this in chemistry?
Because when we deal with electrons, we're dealing with energy. And so I don't know why you guys didn't learn about it.
We learned this in the physics portion.
Okay.
But I failed that.
All right.
That's what I know. I should not take physics.
Yeah.
How do you determine the middle one?
The middle, it will be given to you. But generally, if I had, say if I had a wave, then I'd kind of eyeball it and say, that looks like about the middle. Okay.
Like, can waves be like this one on the top?
No. Here's what they can't do is they can't be like that, if that's what you mean. So we'll say whatever the amplitude is, it's the same. The amplitude's the same here and here. Yeah, good question. But again, we're not going to worry about amplitude in here. Okay. Wavelength. We already talked about how to find wavelength, but the unit that we're using is lambda. So those of you who've watched Revenge of the Nerds, you might know about the tri-lambs. Okay. You'll see me represent lambda or wavelength like that instead of this. Some people say, that looks like a dinosaur. I'm like, okay. Whatever that helps you remember, that's fine.
Upside down Y.
Or an upside down remirrored Y, yeah. But
Chicken nugget dot next to it.
a chicken nugget.
Really does.
Okay. All right, and then when we talk about
Like a dinosaur shaped chicken nugget.
some of you, all right, shh.
Keep them at it.
Now, when we talk about a wave having more energy, it's because it has a high frequency and a short wavelength. So if we're looking at something that has lower energy, okay, then that means it has low frequency and actually long wavelengths. Okay. So vice versa. We'll talk about that a little bit more tomorrow. Give you a little more explanation. Okay. And again, don't really care about the amplitude there. Now, you've all hopefully heard about Roy G. Biv.
Yeah.
Okay. So the red, orange, yellow, green, blue, indigo, violet. And in the lab, we have seen a yellow fire and we have seen a blue fire. Okay. So the red, is that a cool flame or a hot flame? Cool, because on this side we have low energy for the light, and over here it's higher energy. Okay.
Is that like the Hollywood?
We, on the Bunsen burner with methane, we cannot, but we will have a lab where we'll get to see these colors over here. Okay. So next week, I'll do a demo. I don't really trust too many people. Yeah. So on the left side, the lower energy light. On the right side, the higher energy light. And this will have more significance tomorrow when we do some calculations with that. But also, I gave a nice little graphic here to help illustrate all the types of light that we have. Actually, let me move it up a little bit. So all the types of light. And notice that a very small portion of that is visible to us. So like radio waves, that's going through you right now, we can't pick that up because we don't have a transmitter to pick that up. And then gamma rays, luckily we don't have any gamma rays here. Makes me angry. The Incredible Hulk.
Hey, I know.
Yeah.
So, do you ever have to memorize like those waves?
Oh yeah.
'Cause
So you'll know that radio waves is the lowest and that gamma is the highest.
there's a music video, and that song is stuck in my head. It's been in there since 7th grade.
What?
Like, it's a song, and it's awesome. We learned it in 7th grade at Avon. Mr. Osen.
Okay, well, sing it for us.
Yeah.
Radio waves, microwaves, infrared, radiation, visible light, ultraviolet, X-rays, gamma rays.
Wow. Oh
Right, that's impressive.
yeah. Okay. That was just recorded, so all right. Yeah. All right. So to refresh your memory from before that traumatic incident, red has the lowest energy because it has longer wavelengths and a low frequency. Violet has the highest energy because its wavelengths are shorter and we have more of them. Now, did I say what all these travel at?
Nope.
They all travel the same speed. The speed of light. Very good.
Slide down.
Okay.
Yeah.
All right.
Good job.
All right. Yeah, Tristan.
Why are the colors in that?
That's the way God made it. Yeah, and actually, that's a good point. Now, hang on. My wife teaches kindergarten at Maple, and they always, at least inevitably throughout the year or sometime during the year, they draw a rainbow in their class. And I'll walk in and I'll go, "What are you doing putting red next to blue?" I'm like, "Seriously, kids don't know Roy G. Biv?" So there's a, like, they're kindergarten, really. It's like, what are they teaching those kids in Avon? Good night. Stupid children. Alright. Energy of light depends upon a couple things here. The length of exposure. So, like, if you haven't been outside all year and you're like, it's a really nice sunny day here on July 4th. I'm going to go outside for 8 to 10 hours and see how that works out. Okay, probably wouldn't be a good idea. So the length of exposure, the area of exposure, in other words, as you look at my hand and the shadow behind it, what happens to the shadow as I get closer?
It's smaller!
Gets smaller? Wow. Gets bigger because I'm actually capturing more photons that way. Yeah. Or I can actually take those photons and center it in. That's hot. Yeah, not. No.
That is savage.
If it were the sun, that would be different, but this, no. The frequency of light, so whether we're looking at, say, low energy versus high energy light, that also depends on how much energy we're going to have. All right, Planck. Yeah.
I just made a music video for class. I just realized that. Let me get this down.
You have a light that we don't have? Packet? Okay. Now, Planck, we don't need to know the guy's name. We don't care what he did, but we do care about his constant. Okay? So Planck's constant is something that will be given to you. You have to know how to use it. And what this is used in the energy calculation for waves. And let me scroll that up a little bit. What's the matter? Okay. So when we look at E, E is the energy. Now, in here, we don't talk about calories. We don't talk about BTUs. We talk about joules. Okay? A joule is a unit of energy. Okay? And we'll talk about kilojoules later on, but today we're just talking about joules. And it's very similar. There's actually 4.184 joules in every calorie. We don't care about that. We're never going to do any conversions between those. Too many. And so that is energy. And here's Planck's constant, which is 6.626 times 10 to the negative 34 joule second. And that is a constant. And it has a funky unit. Joule times second. All right? That is a negative 34. Sorry, it doesn't show up very well. But it's also right here. Okay. And then the V, what does the V represent again? Frequency, very nice. And what's the unit for frequency? 1 over seconds, not the variable.
Good job.
Okay, so those are the units that we'll be using today, and actually for the next couple days. Now, if I were to ask you, because since Planck's constant is a constant, if I were to ask you to calculate frequency, how would you rearrange that equation with only 3 variables to solve for frequency? How would you rearrange it?
Solve for frequency? Oh, you do E divided by H.
So we're going to divide H on both sides, and we'll have that. Okay? So that's the 2 ways, only 2 ways that you can have this equation. Now, when you start a problem, be sure that you either show it this way or this way to start off. And make sure you know which variable you're looking for. So if you're looking for the frequency, start with that. If you're looking for the energy, start with that. What's that?
Doesn't it feel like, so if you have seconds.
Joule second.
Divided by
Second.
1 second.
So if you divide by a single second, you mean like have it right here?
Yeah.
We're left
You
with
put
joule,
the
joule.
calculator.
Units raw.
No, land off.
Simplify it for
Daryl, I can't help Daryl.
Why would you laugh at me?
Alright, the last thing I want to talk about are nodes. And when we talk about a node, it's dealing with a wave with no height. So like for example, how many waves do I have represented there?
One.
One and a
That is dumb.
1.5? Yeah.
Yeah.
So in other words,
1.5.
you start here, go all the way up, all the way down, and then return back. So that's one wave. Now we're going all the way up, but we don't go back down. Okay? So when we talk about a node is a point where there is no amplitude or no height. So where it intersects, that's considered a node. Let's use a different color.
Oh.
So there's a node, there's a node, there's a node, there's a node. So how many nodes on that 1.5?
7.
4, very good. Okay. So, all right, Jack, you ready for this?
Yeah, wake up, son.
What in the world?
This is hurts.
All right, here you go. Jack, how many waves do we have?
Enough. 18 notes.
No. I'm asking waves.
8.5.
8.5.
So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 waves. How many nodes do we have?
18.
So we have 8 of those. So 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Good job on the 18.
How'd you know that?
He doesn't know. Alright, so questions on how to determine how many nodes you have. Again, it's the point where there is no height or depth. Okay. Alright, let's do a practice problem.
technically it's not a wave.
Alright, so let's take a look at this. Our one and only practice problem, and then your homework is right below. It says calculate the energy of a quantum of light. Ooh, quantum of light, also known as a photon.
That's why I was that.
So, calculate the energy of a photon of light that has a frequency of 3.45 times 10 to the 16 hertz. What should you do with that unit hertz? Don't write HZ within the problem, but change it to
Oh, no, it's second.
1 over second. 1 over seconds. Okay? Now, should we use that equation or rearrange that equation?
Rearrange that. No.
Wait, wait,
Right there. What are you doing?
Use the energy.
Use that equation. Good. So since we already have Planck's constant, which is a constant, doesn't change, joule second, and then I'll multiply it times my frequency, which is 3.45, 10 to the 6. Now, I'm going to be clever here and not write 1 over seconds. I'm going to put seconds right below it. And that's spiffy. So what happens to the unit seconds? Cancel out. What unit remains? Joule, which is energy.
Joule.
So again, let your units talk to you.
Whoa, wait, there's a naked number.
There are no naked numbers. This is 3.45 times 10 times 10 to the 16 1 over seconds, and here's joule seconds. So our energy is some number in joules.
What are you dividing all that by?
What am I by second?
And not 1.
Instead of writing this 1 over seconds here, instead of putting that in there, I just put the seconds on the bottom. Isn't that clever?
It's like a duck.
Who was making all this?
And anybody get a number?
Half-black.
We do that again.
So my calculator says 2.2859. So sig figs.
So like, do you always divide by just one?
What do you mean divide by 1?
Because you have seconds on the bottom, so that's like.
Well, again, that unit for this is 1 over seconds. So instead of just putting it there, I put it like that.
Dividing by seconds.
I'm dividing by second in this case.